Hey, welcome to Pre-Calc Chapter 6. This is Lesson 6.1, Vectors in the Plane, and we'll be talking about vectors pretty much this whole chapter. I also wanted to remind you before we get started here that as we're going along, if something doesn't make sense to you, remember that you can always rewind and watch it again. Remember also that you can pause it whenever you need to. If you need to check something or verify something for yourself, do that. And if you have questions as you go along, pause the video, write it down on your paper, and come back to it either during class when we can see you and answer your questions, or it might be answered later as you go through the notes. So just remember your good note-taking skills. All right, we want to start talking about vectors in general here. Some things can't be represented by a single real number. Force and velocity are two of these, and they have magnitude and direction. It's like if you were taking a trip, you wouldn't just say, oh, I went 60 miles. You would also say which direction you went. Otherwise, it doesn't make sense to people where you went. It could be a number of places. So vectors are simply directed line segments. They have an initial point where they start. That's called the tail. And the terminal point, which is the head. So a lot of times we refer to this as the tail and this as the head. And you can see in our picture over here that the initial point on this vector here is P, and the terminal point is Q. So it's headed in the direction of Q, and it's starting at P. Now there are a couple other things that we need to know about them. Of course, that's the two things. The direction that it's going, we will talk about angles, but we also talk about length. Well, the length of a vector is called a magnitude, and magnitude just means the length or the distance from P to Q. And we would write it like this. Kind of looks like an absolute value, and just remember that magnitude simply means the length of the vector, how far it is. Now, if we have a vector v, sometimes we just want to use one little letter to represent a vector, and v obviously is a good choice, but it could represent this vector that goes from P to Q. Kind of looks like a ray, but we will often use just one little letter to represent it. Okay, and then vector representation by directed line segments. So here we're going to investigate some of these, and I may refer back to that other picture that we had on the slide just before. Let U be represented by the directed line segment from. I'm going to start plotting these. P is at 0, 4. Okay, so there's P. And Q is at -3, -4. So here's Q. And it goes from P to Q. So I put the arrow at Q. Okay, and then let V be represented by the directed line segment from 3, 3. So that's R. To S, which is at 0, -5. And there's S, and it's headed towards S. Show that U is equal to V. Show that the vectors are equivalent to each other. Well, if two vectors are equivalent, we have to check two things. We have to check direction, and we also have to check magnitude. So we're going to be checking both of those things. Okay. Now you're going to see a formal definition of magnitude, or a formula for magnitude, in the next part of our videos, but this is something that you've been doing for quite a while, and you can think about it geographically, or you can think about it using the distance formula or Pythagorean theorem. They're derived from the same thing. Okay, so I'm going to kind of make my little right triangles out of these guys. And I can see that what we call our horizontal component, or the left and right component of vector PQ, is just 3 units. And the vertical component, or the change in the y values is 4 and 4, so that's 8. This one is also 3 for that direction and 8 in that direction. So you can see that they're identical right triangles. You know that the lengths are going to be the same. In fact, if you want to know the magnitude of PQ, kind of think of this like the Pythagorean theorem. It would be the square root of 3 squared plus 8 squared. So that's 64 plus 9, and that is 73. And it would be exactly the same thing for RS, the magnitude of RS. Same thing, 3 squared plus 8 squared, and that's the square root of 73. So we have shown that they do have the same magnitude. Now in terms of direction, we have to pay attention to where the arrows are. They are both pointing generally down, and you can also see that they have the same slopes. The slopes for both of them are 8/3, the rise over the run, but they are going in that same general downward direction. So these two vectors are equal to each other. They are equivalent. They have the same magnitude and the same direction.